In the beginning, when God created the heavens and the earth was a formless void. Book of Genesis, Book 1, Chapter 1. We should all be grateful for dramatic changes to global climate. Were it not for billions of years of intense celestial and solar activity, repeated asteroid strikes, epic volcanic eruptions, extraordinary atmospheric change, spectacular tectonic shifts, and constant biotic adaptation, we would not be alive today. Astrophysicists talk of habitable regions around stars that are not too hot and not too cold as being in the Goldilocks zone. The Earth is one of many such examples. But conditions have changed constantly and sometimes catastrophically since the creation of our planet around 4.6 billion years ago. For almost all the time that the Earth has existed, our species would not and could not have survived. In today's world, we think of humans as architects of dangerous environmental and climate change, but we are prime beneficiaries of such transformations in the past. Our role on this planet has been an exceptionally modest one. The first hominins appeared only a few million years ago, and the first anatomically modern humans, including Neanderthals, around 500,000 years ago. What we know of the period since then is patchy, difficult to interpret, and often highly speculative. As we get closer to the modern day, archaeology helps us understand more reliably how people lived. But to know what they did, thought, and believed, we have to wait till the development of full writing systems around 5,000 years ago. To put that into context, accounts, documents, and texts that allow us to reconstruct the past with nuance and detail cover around 0.0000001% of the world's past. We are not just fortunate to exist as a species, but in the grand scheme of history, we are new and very late arrivals. Like rude guests who arrive at the last minute, cause havoc, and set about destroying the house to which they've been invited, human impact on the natural environment has been substantial and is accelerating to the point that many scientists question the long-term viability of human life. That in itself is not unusual, however. For one thing, our species is not alone in transforming the world around us. For other species of biota, that is to say flora, fauna, and microorganisms, are not passive participants in or simple bystanders to a relationship that exists solely or even primarily between humans and nature. Each is actively involved in processes of change, adaptation, and evolution, sometimes with devastating consequences. This is one reason why some scholars have criticized the idea and the name of the Anthropocene, which prioritizes humans into a distinguished species that has claimed the right to identify what is and is not wild, to classify resources as ones that can be used, sustainably or otherwise. Such, some argue, is the arrogance that greatly overestimates human contributions while downplaying those of other life forms, almost at the point of non-existence. For around half the Earth's existence, there was little or no oxygen in the atmosphere. Our planet was formed through a long period of accretion, or gradual accumulation of layers, followed by a major collision with a Mars-sized impactor, which released enough energy to melt the Earth's mantle and create the earliest atmosphere from the resultant exchange between a magma ocean and vapor that was anoxic, that is to say, lacking in oxygen. The Earth's biogeochemical cycles eventually resulted in a radical transformation. Although there is considerable debate about how, when, and why oxygenic photosynthesis occurred, evidence from organic biomarkers, fossils, and genome-scale data suggests that cyanobacteria evolved to absorb and take energy from sunlight, using it to make sugars out of water and carbon dioxide, releasing oxygen as a byproduct. New models suggest that 1 to 5 billion lightning flashes that occurred per year on early Earth may have been the source of large volumes of prebiotic reactive phosphorus that played an important role in the emergence of terrestrial life. Around 3 billion years ago, if not earlier, enough oxygen was being produced to create oases in protected, nutrient-rich, shallow marine habitats. Whether because of chemical reaction, evolutionary development, sudden superabundance of cyanobacteria, volcanic eruptions, or a slowdown in the Earth's rotation, or a combination of all five, atmospheric oxygen levels accumulated rapidly around 2.5 to 2.3 billion years ago, resulting in an episode known as the Great Oxidation Event. This was a key moment that paved the way for the emergence of complex life as we know it. It also led to dramatic changes in climate, as rapidly increasing oxygen reacted with methane, producing water vapour and carbon dioxide. Alongside the effects of a supercontinent being formed from the collisions of land masses, the Earth's greenhouse was weakened, leading to the planet being covered completely in ice and snow. Changes in the Earth's orbit around the Sun, known as the Milankovitch cycle, may also have played a role in this process. So too might giant meteorite impacts, which not only threw up debris into the atmosphere that blocked the Sun's light and heat, but also played an important role in the formation of the continents. The glacial episodes may have been weaker or stronger over the course of several 100 million years, but in general, the effects of Snowball Earth were so dramatic that some scientists refer to this period as a whole as a climate disaster. This process was precarious and complex and is the subject of considerable advances in current research. As with later glaciations, however, it resulted in profound changes for the planet's plant and animal life. One outcome appears to have been the evolution of small organisms into larger sizes, capable of moving at faster speeds to compensate for the high viscosity of cold seawater. It has recently been suggested that the formation of 8,000-kilometre-long belts of supermountains may have played a role in the rise of atmospheric oxygen and in stimulating biological evolution as a result of phosphorus, iron and nutrients being deposited into oceans as mountains eroded over the course of hundreds of millions of years. The fossil record of complex, macroscopic organisms begins with the Ediacara biota period, which started 570 million years ago, and which saw at least 40 recognized species developing into multicellular animals that were symmetrical, presumably helpful for functions such as mobility. It marked a period of extraordinary diversification in the variety of animals living in the oceans and in their evolution, development, and adaptation, with some creatures, like trilobites, developing respiratory organs on their upper limbs. Near the end of the Ordovician period, around 444 million years ago, a sudden cooling, perhaps triggered by tectonic shifts that produced the Appalachian Mountains, led to sharp falls in temperature and initiated shifts in deep ocean currents, as well as declines in sea level that shrank habitats for marine planktonic and nectonic species. That cooling produced one pulse of extinction. Another came when temperatures moderated, sea levels rose, and ocean current patterns stagnated, with a resultant sharp fall in oxygen levels. Traces of mercury and indications of significant acidification suggest that volcanic activity was a key factor in the second stage of a process that ultimately brought about the extinction of 85% of all species. This was just one of several spectacular episodes that wiped out life for all but a small proportion of living organisms. The Moon may have played a part in the changes in the millions of years that followed. Formed from debris thrown into space at the time of the impact that created the Earth, the Moon has a gravitational pull that plays a major role in ocean tides. As such, it is responsible for the flows that help transport heat away from the equator and towards the poles, fundamentally shaping Earth's climate. As the Moon used to be much closer to the Earth, perhaps half the distance away that it is today, these forces were considerably stronger and therefore had a greater impact on the Earth's climate and also perhaps on its wildlife. Recent modelling suggests that big tidal ranges may have been responsible for forcing bony fish into shallow pools on land, thereby prompting the evolution of weight-bearing limbs and air-breathing organs. The Moon played a role not only in the transformation of the Earth, in other words, but also in the development of life on this planet. It still exerts an important influence. The reproductive cycles of many marine creatures are closely synchronized with lunar phases, with migration and spawning in fish, crab, and plankton species triggered by the Moon's glow. Coral genes change their activity level according to the waxing and waning phases of the Moon. Lunar phases seem to influence the timing of the mating season of wildebeest in the Serengeti and have been linked to spontaneous delivery in cows. Many primates become more active at night during a full moon, perhaps because higher light levels offer greater chances of predator evasion. It has been noted too that albatrosses are more active on moonlit nights. Though little studied, lunar phases and moonlight seem to be closely connected to the annual migrations of billions of seasonal animal species, especially birds, whose fueling opportunities are heavily light-dependent. Indeed, there seem to be important links between human behaviour, activity, and even fertility and lunar rhythms. Studies of indigenous communities in Argentina that do not have access to electricity, and therefore offer helpful control conditions, show that sleep starts later and is shorter on nights before the full moon, when moonlight is available in the hours following dusk.